Have you ever wondered how your machine can seemingly stream a high-def video, download a massive file, and run a heavy video game all at the exact same time without missing a single beat? Well, it's not actually doing it all at once. The secret lies in a highly complex, totally invisible process called CPU scheduling. It's the engine of your computer, and we're going to demystify it right now in this explainer.
Okay, let's set the stage with a little thought experiment to understand the core paradox of a single CPU trying to juggle multiple processes perfectly. Imagine this. You've got one single chef and 100 hungry customers. That chef can't actually cook every single meal simultaneously, right? They have to rapidly switch between chopping vegetables, searing steaks, and plating desserts, giving the grand illusion that everything is being prepared at exactly the same time. Your computer's central processing unit operates on that exact same principle. It's constantly deciding which task gets its attention next so that your entire system doesn't just crash to a halt. To truly master this invisible engine, we have a solid roadmap today. We'll be covering 1. The CPU scheduling paradox. 2. The rules of the game. 3. The flaw in fairness. 4. Predicting the future. 5. The starvation problem. And finally, 6. Real-world multi-level queues.
Section 1. The CPU scheduling paradox. So here is the big picture. Like we established, computers don't actually do everything at once. What's really happening is process execution consists of a rapid, continuous cycle. It's constantly alternating between CPU execution, which we call a CPU burst, and I/O waiting. Think of it like this. A program intensely crunches some heavy math on the CPU, and then it pauses. It has to wait to read a file from the hard drive, or wait for you to click your mouse. The CPU literally cannot afford to sit idle during that wait. It has to instantly snap to another process.
Section 2. The rules of the game. To manage this relentless, microsecond by microsecond cycle, a specific piece of the operating system called the CPU short-term scheduler steps onto the field. Its entire job is making crucial, split-second decisions to allocate the CPU core to a process waiting in the ready queue.
Now, this brings us to a massive battle of paradigms. On one side, we have non-preemptive scheduling. This is where a process basically hoards the CPU. Once it grabs control, it is not letting go until it finishes or voluntarily decides to wait. On the flip side, we've got preemptive scheduling. This is where the system has the absolute authority to forcibly interrupt a running process and hand the CPU over to something more urgent. It's incredibly responsive, sure, but man, it requires some incredibly careful coordination so you don't corrupt shared data when you yank the CPU away mid-calculation.
So once the scheduler decides who goes next, the actual physical handover is executed by a module called the dispatcher. It does 3 exact steps. It switches the context, it switches the system into user mode, and it jumps to the exact right memory location to restart the user program. And listen, this dispatcher has to be lightning fast. Every single microsecond it takes to stop one process and start another is entirely wasted time. We call that delay dispatch latency. Section 3. The flaw in fairness. Let's look at the most obvious way you might organize things. First come, first serve. It seems perfectly fair, right? Whoever asks first gets it first. But mathematically, this hides a fatal flaw.
Let's imagine a scenario to brilliantly illustrate this flaw. Say process 1 arrives first, and it's an absolute beast. It needs a massive 24 time units to complete its CPU burst. Right behind it are process 2 and process 3, and they only need a quick 3 units of time each. Because first come, first serve is non-preemptive, those quick little jobs are completely, hopelessly blocked.
And because those quick jobs are stuck behind the massive one, the wait times get heavily skewed. Process 1, it waits 0 milliseconds. Awesome for process 1, but process 2 has to sit there for the full 24 milliseconds, and process 3 waits 27. When you average that out, the waiting time across the board skyrockets to an agonizing 17 milliseconds. Computer scientists call this counterintuitive phenomenon the convoy effect. Just picture one painfully slow, heavy truck on a one-lane highway with a dozen fast sports cars trapped right behind it, honking their horns. It proves a really surprising insight. Simply waiting fairly in a first-come, first-served line is actually a terrible strategy for overall computer efficiency. It just leads to bottlenecked CPUs and incredibly frustrated users. Section 4. Predicting the future. To evolve past that awful convoy effect, we move to a strategy called shortest job first. This algorithm entirely abandons human fairness and ruthlessly prioritizes throughput by jumping the shortest tasks to the absolute front of the line. And wow, does it optimize things. By preemptively cutting in whenever a shorter task arrives, the system drops the average wait time for a similar set of processes all the way down to just 3 milliseconds. Mathematically speaking, shortest job first is literally the optimal algorithm for minimizing average wait time. But there is a huge, almost impossible catch here. To know which job is the shortest, a computer essentially has to predict the future. It needs to know exactly how long a process is going to take before it even runs it. Since it obviously can't just ask the user, the operating system attempts to predict the future using an estimation technique called exponential averaging, which relies on this wild mathematical formula. Okay, let's break this complex math down simply, like we're starting from scratch. The system is basically making a highly educated guess. It takes the actual length of the most recent CPU burst, and it blends that with its own previous predictions. By using a weight variable, usually set right down the middle at 1/2, the formula beautifully combines the hard reality of what just happened with the historical trend of all past predictions, spitting out a really solid guess for the next birth length. You can really see this magic happen when you graph it out. If you have a rigid, erratic line bouncing around representing the actual unpredictable CPU bursts, the algorithm's mathematical guesses form this smooth curve that constantly chases it. As time moves forward, that mathematical guess smoothly catches up to and tracks the rigid reality. Because it gives less weight to older history, the system can rapidly adapt to new behaviors without completely getting amnesia about the past. Section 5. The starvation problem. Because as it turns out, prioritizing only the absolute fastest tasks introduces a very dark side to scheduling. If a constant, endless stream of short, snappy tasks keeps arriving in the ready queue, a long, low-priority job is going to suffer from what computer scientists ominously call CPU starvation. It just gets continuously pushed to the back of the line, practically freezing in the system forever, completely neglected. So, what's the ultimate fix to this digital starvation? It's a clever technique called aging. This is a built-in mechanism where the operating system slowly, over time, bumps up the priority of a neglected task. Even if a process starts at the absolute rock-bottom lowest priority, if it waits long enough, aging guarantees it will eventually become the most important task in the entire system. It absolutely will finally execute. Now, another powerful way to dodge starvation entirely is round-robin scheduling. This approach completely abandons strict priority and all that future-predicting guesswork. Instead, it relies on strict preemptive equality. It hands every single task a rapid time quantum, usually a tiny sliver of time, like 10 to 100 milliseconds. Once a process's tiny slice of time is up, boom, a timer interrupts it and it goes straight back to the end of the line. It's incredibly fair, making it perfect for systems where users need real-time, snappy responses. Section 6, Real-World Multi-Level Queues. So, looking at everything we've unpacked, how do real, modern operating systems actually handle these totally contradictory algorithms today?
Well, they don't just pick one. They build a Frankenstein hybrid called multi-level feedback queues. Instead of one single line, they partition tasks into distinct levels. You might have a high-priority foreground queue running round-robin for snappy interface stuff, and a background queue running first-come, first-serve for heavy, invisible tasks. And crucially, these queues are dynamic. A process isn't stuck forever. It can age and upgrade to a higher queue if it's starving, or it can be brutally demoted to a lower queue if it starts hogging way too much CPU time. Which brings us to a final provocative question. As our systems constantly balance this brutal efficiency against complex fairness, are we really in control? Or are our computers just making incredibly fast, educated guesses to maintain this seamless illusion of simultaneous reality? Behind your screen is a massive mathematical tug-of-war happening millions of times a second. So the next time you effortlessly multitask, just ponder how this delicate, ongoing, algorithmic balancing act quietly shapes our entire digital existence. Thanks for joining me on this explainer.